A breeder reactor is a nuclear reactor that generates more fissile material than it consumes. These devices achieve this because their neutron economy is high enough to breed more fissile fuel than they use from fertile material, such as uranium-238 or thorium-232. Breeders were at first found attractive because their fuel economy was better than light water reactors. But interest declined after the 1960s as more uranium reserves were found, and new methods of uranium enrichment reduced fuel costs, fuel efficiency and types of nuclear waste. Breeder reactors could, in principle, extract almost all of the energy contained in uranium or thorium, decreasing fuel requirements by a factor of 100 compared to widely used once-through light water reactors, which extract less than 1% of the energy in the uranium mined from the Earth. The high fuel efficiency of breeder reactors could greatly reduce concerns about fuel supply or energy used in mining. Adherents claim that with seawater uranium extraction, there would be enough fuel for breeder reactors to satisfy our energy needs for 5 billion years at 1983's total energy consumption rate, thus making nuclear energy effectively a renewable energy. Nuclear waste became a greater concern by the 1990s. In broad terms, spent nuclear fuel has two main components. The first consists of fission products, the leftover fragments of fuel atoms after they have been split to release energy. Fission products come in dozens of elements and hundreds of isotopes, all of them lighter than uranium. The second main component of spent fuel is transuranics, which are generated from uranium or heavier atoms in the fuel when they absorb neutrons but do not undergo fission. All transuranic isotopes fall within the actinide series on the periodic table, and so they are frequently referred to as the actinides. The physical behavior of the fission products is markedly different from that of the transuranics. In particular, fission products do not themselves undergo fission, and therefore cannot be used for nuclear weapons. Furthermore, only 7 long-lived fission product isotopes have half-lives longer than 100 years, which makes their geological storage or disposal less problematic than for transuranic materials. With increased concerns about nuclear waste, breeding fuel cycles became interesting again because they can reduce actinide wastes, particularly plutonium and minor actinides. Breeder reactors are designed to fission the actinide wastes as fuel, and thus convert them to more fission products. After spent nuclear fuel is removed from a light water reactor, it undergoes a complex decay profile as each nuclide decays at a different rate. Due to a physical oddity referenced below, there is a large gap in the decay half-lives of fission products compared to transuranic isotopes. If the transuranics are left in the spent fuel, after 1,000 to 100,000 years, the slow decay of these transuranics would generate most of the radioactivity in that spent fuel. Thus, removing the transuranics from the waste eliminates much of the long-term radioactivity of spent nuclear fuel. Today's commercial light water reactors do breed some new fissile material, mostly in the form of plutonium. Because commercial reactors were never designed as breeders, they do not convert enough uranium-238 into plutonium to replace the uranium-235 consumed. Nonetheless, at least one-third of the power produced by commercial nuclear reactors comes from fission of plutonium generated within the fuel. Even with this level of plutonium consumption, light water reactors consume only part of the plutonium and minor actinides they produce, and non-fissile isotopes of plutonium build up, along with significant quantities of other minor actinides. Conversion ratio, break-even, breeding ratio, doubling time, and burnup. One measure of a reactor's performance is the conversion ratio. All proposed nuclear reactors except specially designed and operated actinide burners experience some degree of conversion. As long as there is any amount of a fertile material within the neutron flux of the reactor, some new fissile material is always created. The ratio of new fissile material in spent fuel to fissile material consumed from the fresh fuel is known as the conversion ratio, or breeding ratio, of a reactor. For example, commonly used light water reactors have a conversion ratio of approximately 0.6. Pressurized heavy water reactors running on natural uranium have a conversion ratio of 0.8. In a breeder reactor, the conversion ratio is higher than 1. Break-even is achieved when the conversion ratio becomes 1. The reactor produces as much fissile material as it uses. Doubling time is the amount of time it would take for a breeder reactor to produce enough new fissile material to create a starting fuel load for another nuclear reactor. This was considered an important measure of breeder performance in early years, when uranium was thought to be scarce. However, since uranium is more abundant than thought, and given the amount of plutonium available in spent reactor fuel, doubling time has become a less important metric in modern breeder reactor design. Burnup is a measure of how much energy has been extracted from a given mass of heavy metal in fuel, often expressed in terms of gigawatt-days per ton of heavy metal. Burnup is an important factor in determining the types and abundances of isotopes produced by a fission reactor. Breeder reactors, by design, have extremely high burnup compared to a conventional reactor, as breeder reactors produce much more of their waste in the form of fission products, while most or all of the actinides are meant to be fission and destroyed. In the past, breeder reactor development focused on reactors with low breeding ratios, from 1.01 for the shipping port reactor running on thorium fuel and cooled by conventional light water to over 1.2 for the Soviet BN-350 liquid metal-cooled reactor. Theoretical models of breeders with liquid sodium coolant flowing through tubes inside fuel elements suggest breeding ratios of at least 1.8 are possible. The Soviet BR-1 reactor achieved a breeding ratio of 2.5. Types of breeder reactor. Many types of breeder reactor are possible. A breeder is simply a reactor designed for very high neutron economy with an associated conversion rate higher than 1.0. In principle, almost any reactor design could possibly be tweaked to become a breeder. An example of this process is the evolution of the light water reactor, a very heavily moderated thermal design, into the superfast reactor concept, using light water in an extremely low-density supercritical form to increase the neutron economy high enough to allow breeding. Aside from water-cooled, there are many other types of breeder reactor currently envisioned as possible. These include molten salt-cooled, gas-cooled, and liquid metal-cooled designs in many variations. Almost any of these basic design types may be fueled by uranium, plutonium, many minor actinides, or thorium, and they may be designed for many different goals, such as creating more fissile fuel, long-term steady-state operation, or active burning of nuclear wastes. For convenience, it is perhaps simplest to divide the extant reactor designs into two broad categories based upon their neutron spectrum, which has the natural effect of dividing the reactor designs into those designed to use primarily uranium and transuranics, and those designed to use thorium and avoid transuranics. Fast breeder reactor, or FBR, uses fast neutrons to breed fissile plutonium and possibly higher transuranics from fertile uranium-238. The fast spectrum is flexible enough that it can also breed fissile uranium-233 from thorium, if desired. Thermal breeder reactor use thermal spectrum neutrons to breed fissile uranium-233 from thorium. Due to the behavior of the various nuclear fuels, a thermal breeder is thought commercially feasible only with thorium fuel, which avoids the buildup of the heavier transuranics. Reprocessing. Fission of the nuclear fuel in any reactor produces neutron-absorbing fission products. Because of this unavoidable physical process, it is necessary to reprocess the fertile material from a breeder reactor to remove those neutron poisons. This step is required if one is to fully utilize the ability to breed as much or more fuel than is consumed. All reprocessing can present a proliferation concern, since it extracts weapons-usable material from spent fuel. The most common reprocessing technique, PUREX, presents a particular concern, since it was expressly designed to separate pure plutonium. Early proposals for the breeder reactor fuel cycle posed an even greater proliferation concern because they would use PUREX to separate plutonium in a highly attractive isotopic form for use in nuclear weapons. Several countries are developing reprocessing methods that do not separate the plutonium from the other actinides. For instance, the non-water-based pyrometallurgical electrowinning process, when used to reprocess fuel from an integral fast reactor, leaves large amounts of radioactive actinides in the reactor fuel. More conventional advanced, water-based reprocessing systems like PUREX include SANEX, UNEX, DIAMEX, COEX, and TRUEX, as well as proposals to combine PUREX with coprocessors. All these systems have better proliferation resistance than PUREX, though their adoption rate is low. In the thorium cycle, thorium-232 breeds by converting first to protactinium-233, which then decays to uranium-233. If the protactinium remains in the reactor, small amounts of U-232 are also produced, which has the strong gamma emitter TL-208 in its decay chain. Similar to uranium fuel designs, the longer the fuel and fertile material remain in the reactor, the more of these undesirable elements build up. Inside the envisioned commercial thorium reactors, high levels of U-232 would be allowed to accumulate, leading to extremely high gamma radiation doses from any uranium derived from thorium. These gamma rays complicate the safe handling of a weapon and the design of its electronics. This explains why U-233 has never been pursued for weapons beyond proof-of-concept demonstrations. Waste reduction. Nuclear waste became a greater concern by the 1990s. Breeding fuel cycles attracted renewed interest because of their potential to reduce actinide wastes, particularly plutonium and minor actinides. Since breeder reactors on a closed fuel cycle would use nearly all of the actinides fed into them as fuel, their fuel requirements would be reduced by a factor of about 100. The volume of waste they generate would be reduced by a factor of about 100 as well. While there is a huge reduction in the volume of waste from a breeder reactor, the activity of the waste is about the same as that produced by a light water reactor. In addition, the waste from a breeder reactor has a different decay behavior, because it is made up of different materials. Breeder reactor waste is mostly fission products, while light water reactor waste has a large quantity of transuranics. After spent nuclear fuel has been removed from a light water reactor for longer than 100,000 years, these transuranics would be the main source of radioactivity. Eliminating them would eliminate much of the long-term radioactivity from the spent fuel. In principle, breeder fuel cycles can recycle and consume all actinides, leaving only fission products. As the graphic in this section indicates, fission products have a peculiar gap in their aggregate half-lives, such that no fission products have a half-life longer than 91 years and shorter than 200,000 years. As a result of this physical oddity, after several hundred years in storage, the activity of the radioactive waste from a fast breeder reactor would quickly drop to the low level of the long-lived fission products. However, to obtain this benefit requires the highly efficient separation of transuranics from spent fuel. If the fuel reprocessing methods used leave a large fraction of the transuranics in the final waste stream, this advantage would be greatly reduced. Both types of breeding cycles can reduce actinide wastes. The fast breeder reactor's fast neutrons can fission actinide nuclei with even numbers of both protons and neutrons. Such nuclei usually lack the low-speed, thermal neutron resonances of fissile fuels used in LWRs. The thorium fuel cycle inherently produces lower levels of heavy actinides. The fertile material in the thorium fuel cycle has an atomic weight of 232, while the fertile material in the uranium fuel cycle has an atomic weight of 238. That mass difference means that thorium-232 requires 6 more neutron capture events per nucleus before the transuranic elements can be produced. In addition to this simple mass difference, the reactor gets 2 chances to fission the nuclei as the mass increases. First as the effective fuel nuclei U-233, and as it absorbs 2 more neutrons, again as the fuel nuclei U-235. A reactor whose main purpose is to destroy actinides, rather than increasing fissile fuel stocks, is sometimes known as a burner reactor. Both breeding and burning depend on good neutron economy, and many designs can do either. Breeding designs surround the core by a breeding blanket of fertile material. Waste burners surround the core with non-fertile waste to be destroyed. Some designs add neutron reflectors or absorbers.